Okay, so using our log laws, we know the bases are the same. So if we're going to add logs of the same base, we multiply the numbers. So 5 2s are 10. So I end up with a log base 10 of 10. And if the base and the number are the same, well, that's equal to 1. So our final answer is 1. Similar, if we have a subtraction with the same base, we do a division. So log base 4 of 20 over 5 is log base 4 of 4. Numbers are again the same. So I get 1. I guess when we're simplifying our logs, the idea is to try and get our bases and the number inside to be the same ideally. So again, 16 we could write as 2 to the power of 4. And from our log law, I can bring the 4 out the front. So that gives me 4 times log base 2 of 2. Again, the bases are the same. So this time I get 4. Two approaches here. I could, if I wanted to, sort of put everything as sort of log base 3 of 3 cubed plus log base 3 of 3 squared minus log base 3 of 3 to the 4. Absolutely, then bring the numbers out the front and add and subtract. I thought I'd do it just slightly differently. Again, the bases are the same, so I've got an addition, so I can multiply. I've got a subtraction, so I bring that in as a division. And now if I use just a little bit of fraction, 9 goes into 81 9 times, so I end up with 27 on 9, which of course is 3. And again, log base 3 gives me a 1. But we would get there in a similar way. If I finished off the previous style, I'd get 3. Undo that. I get 3 plus 2 minus 4, which is also 1. So we're going to get there the same way. And I guess on these next examples, I've chosen to simplify the expressions first. So 64 is 4 to the power of 3. 16 is 4 to the power of 2. And 256 is 4 to the 4. Right, so again, I can bring the numbers out the front. So I get 3 times log base 4, which is 3 times 1. 2 times 1, 4 times log base 4. So 3 plus 2 minus 4 is, of course, 1. This one's a little bit different. I guess initially I was going to go with, and I have in the past, bringing the 2 in. So I get a 7 squared and a 21 squared. And I'm going to add logs of the same base. So I'm going to end up with 49 times 21 squared, which is a mighty big number. Probably pays off in this case to consider the 21 as being a 7 times 3. And if we're going to multiply within the log, that's the same as adding them separately. So I can rewrite. First term stays the same. I get 2 times log base 3, 7 plus log base 3, 3. That's the key there, isn't it? Log base 3 becomes a 2. Or 2 because I multiply the 2 across. So we can see, hopefully, I've got 2 log base 3, 7 plus 2 log base 3, 7 is a 4 log base 3, 7 plus 2. Finally, it's important to note here I've got 2 separate logs being divided, not the one log with 16 over 64. So if I treat each of those lines separately, 16 is 4 to the power of 2, 64 is 4 to the power of 3, bring the 2 and the 3 out the front, and I get log base 3 4s that can cancel off. So I end up with 2/3. Similarly, it's the 4th root of 1 over 625. So that's 1 over 625 to the power of a quarter. Quarter can come out the front. 1 on 625, or 625 is 5 to the 4. And so that gives me a 5 to the minus 4. So again, the negative 4 can come out the front. Negative 4 times a quarter times the 1, which is the log base 5, gives me a negative 1 in total. Sorry lads, just doing a bit of work. There we go, probably 4. Where's the wheel? Should be alright. Yeah, so we've got period 1 to do revision. Okay, Okay, so the most important thing is just to make sure that the bases are all the same. In this case, they are all base E. And so if we, I guess, look at the left-hand side, bring that 2 back into the power up here to make it an x squared. So we have natural log of x squared minus natural log of x minus 1 on the left. If we subtract natural logs, we divide the actual expression. So that's the equivalent of x squared over x minus 1. So if I have natural log of that expression equal to natural log of another expression, well, we equate, and so both expressions must be equal. So this implies that an x squared over x minus 1 has to equal x minus 4. Multiply the x minus 1 across, expand the terms on the right-hand side, so I'll end up with x squared equal to x squared minus 5x plus 4. Subtract the x squared, so I end up with 5x equal to 4, so x is equal to 4/5. A habit that we have to all get into is then to check to see if that answer is feasible or reasonable in terms of the domain of the function that we're dealing with. So if we have a look at the actual log expressions we've got, natural log of x minus 1, natural log of x minus 4. For each of those to exist, we need the expression inside the log to be positive, which means the domain of that expression is x is greater than 4. So whilst x equal to 4/5 solves that equation algebraically, it's not feasible. So since x value is not greater than 4, there is actually no solution to that. All right, so that's a really important habit to get into. And actually even here, yep, that's fine. So let's go on to B. I guess there's a few ways. We're going to stick to the log laws at this point in time. So again, I'm going to bring the 3 into the x to make it an x cubed. And I'm going to turn 2 into a log expression. And since the bases we're dealing with are base 10, I'm going to make 2 times log base 10 of 10, which is the equivalent of 1. So really, I'm just doing 2 times 1. But then on the next line there, we can see I can bring that 2 into the power to make it log base 10 of 100. So on this line, I've got a sum of log expressions, which means I multiply them together. So I can write on the left-hand side, log base 10 of 100 times x cubed equal to log base 10 of x to the 5. All right, again, bringing the 5 into the power. So log base 10s, the bases are the same. So we can equate the log terms. So that's the equivalent of having 100x cubed equaling x to the 5. Divide by x cubed, we get 100 equal to x squared. Take the square root, I get plus or minus 100. So x is equal to plus or minus the square root of 100, I should say. And x is equal to plus or minus 10. But again, if we check the domain of the equation I'm looking to solve, x has to be greater than 0, which means x equal to positive 10 is the only feasible solution. All right. Down to C, similar process. Okay, we'll bring the 2 into the power. We've got a difference there. Notice the 3 is inside the log expression there, so we'll just leave that as it own. We can't muck around with that in terms of a power. So left-hand side, I'm going to end up with the natural log of x plus 2 all squared over x because there's a difference, which is equal to the natural log of 3x minus 3 if I multiply that bracket out. Again, log terms on the left and the right, so we can equate the expressions inside. So I end up with x plus 2 all squared on x equal to 3x minus 3, multiplied by my x across. And expand on the left, I'll get an x squared plus 4x plus 4 equal to 3x squared minus 3x. What are we going to do? We're going to group our x squareds together. I like to keep the coefficient of x squared to be positive, so I'm going to take everything to the right-hand side to leave me with 2x squared minus 7x minus 4. A little bit of cross method there. 2x and x, 2x times x is a factor of the first term. 1 times negative 4 is what I'm looking for the factors of the second term. Obviously, if I fire down the line there, 2x times negative 4 is minus 8x, plus x times 1, which is plus 1, so it gives me a negative 7x, which is my middle term. So I end up with a 2x plus 1, x minus 4 equal to 0. So x is equal to minus a half and x is equal to 4. But once again, check the domain. And for all of those to exist, I need x to be greater than 1. And so x equal to 4 is the only solution there that satisfies that. Okay, D is a little bit different because if you're not careful, it looks like we can just bring the 2 out the front, but we can't. It's the natural log, sorry, it's log base 4 of x all squared with a 2 out the front. So in actual fact, it's actually a bit of a quadratic expression because we've got a log base 4 of x to the power of 2, as opposed to log base 4 of x squared, which is just the term being squared. So if I put u equal to log base 4x, look, I've been a bit sloppy there, haven't I? So what if I just tidy these up as we go? They should all be u, shouldn't they? If I put u equal to log base 4x, come on, catch up. Sorry about that. So I get a 2u squared equals 3 minus 5u, because I'm going to bring that 5 out the front there this time. Okay, so I get u equal to log base 4x, which means I get 2u squared plus 5u minus 3 is equal to 0. So factors of the first term, 2u and u, factors of the second term, negative 1, 3. 2u minus 1, u plus 3. So we get u is equal to a half and u is equal to minus 3. Now I substitute back for the u term, which is log base 4 of x. And I guess really I've taken a bit of a shortcut here by using my base transformation rule. So we know that if y equals a to the x, well then x equals log base a y. Okay, so that's what I've done. So the base is 4 to the power of a half is equal to x. 4 to the power of minus 3 is equal to x. So we can see that first solution there, 4 to the half equal to x, therefore x is equal to 2. And if we continue on my second solution here, I get 4 to the minus 3 is equal to x. So x is equal to 1 on 64. Okay, so check to see our domains. Both of them just require x to be greater than 0, so both of those solutions are valid. Slide into E now. Let's get my highlighter back. So again, what have we got? We've got the natural log of x. So I'm going to bring the 2 into the power. So, and then again, I've got natural log on one side, natural log on the right-hand side. So I can equate the expressions. So x is equal to 2 minus x squared. Expand 4, a squared minus 2ab plus b squared. And group my terms together. So x squared minus 5x plus 4. Factorising to leave me with x is equal to 4 or 1. But again, in the second expression there, I'm going to need x to be less than 2. Because at x equal to 4, I get 2 minus 4, and I can't work out the natural log of negative 4. So that only leaves me with x equal to 1 to be a valid solution. F is similar to the one we did in D, where I've got log base 2 of x all squared. So if I put u equal to log base 2 of x, I end up with u squared minus 3 minus 2u. So a u squared plus 2u minus 3 equal to 0. Factorise, I get u plus 3, u minus 1. So u is equal to negative 3 and 1. So again, log base 2 of x is equal to negative 3. Log base 2 of x is equal to 1. So again, I've used the log base transformation, I guess. So if we look at the blue one, 2 to the power of negative 3 is equal to x, which is that expression. And then 2 to the power of 1 is equal to x. So I get x is equal to 2 to the minus 3, which is 1 over 2 cubed, which is 8, and 2. Again, as long as x is greater than 0, both those solutions are valid, so we can keep both of those in. Multiple choice. What have we got? We've got f of x equals 3, natural log of 2x. Now, if f of 5x is equal to natural log of y, then, all right, so let's work out what. f of 5x is, if I substitute it into my function, that's the same as 3 a log base e of 2 times 5x, which is log base e of 10x to the power of 3. The left-hand side, f of 5x is equal to log ey, so I can put log ey on the left-hand side equal to log e 10x to the power of 3. So again, I can equate expressions, so that means y is equal to 10x to the power of 3, which is 1000x cubed, which is e.